Sorry, 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 sorry. Test. So, whoa, this is loud. Let me start today's introductions. It's my great pleasure to have Bruce Gaulin here with us. Bruce is a distinguished professor at McMaster University in Hamilton, Canada. Bruce has a distinguished career. He's served as a president of the American Neutron Scattering Society. Is that the correct title? Yeah, Neutron Scattering Society. Okay, I stand corrected. That's right. He also served at the equivalent position in Canada. I dare not pronounce what that sounds like. More recently, he was visiting University of Paris-Saclay, where he was the Jean d'Alembert Chair of Physics. So the same D'Alembertian that, I don't know, for those of you who take E&M, you know, the little square symbol, that was Jean d'Alembert. And in his distinguished career, Bruce has done many interesting things, and all of them revolve around the questions of what happens to spins when they're arranged in a lattice, where they can all be happy. Right? So it's, in many ways, today is going to be the story about unhappy spins. Please go ahead.
Thanks very much, Andre, and yes, thank you very much for the invitation to come here. Actually, I know probably about half of the condensed matter physics group here. Pen Chang I've known forever, and Amelia, of course, I've known and respected for a while as well. So anyway, it's a department I've long admired, so I'm very happy to get the chance to visit. Yeah, so as Andre was saying, I'm going to be talking about unhappy magnets, but unhappy magnets that can generate very interesting quantum disordered ground states. At least that's what we'll be looking for. And the place we'll be looking for them is in these cerium-based pyrochlore materials. And so this is a story. This particular story goes back about 6 or 7 years for me. But our studies of materials based on these architectures actually goes back to around 1990 or so. Okay. Yeah, so because this is a collaboration which has gone on for 6 or 7 years, and because it's involved material synthesis and crystal growth and advanced characterization by neutron scattering and other techniques, and also by very important theoretical contributions that allow us to understand the measurements, I've got a lot of collaborators. This is just the nature of the beast in this sort of thing. And it's mostly a very good thing. So this includes what I'm going to call my group at McMaster, although it also involves some of my colleague professors who probably wouldn't appreciate being called part of my group. Also there's a rather large group of collaborators who have contributed different things. This group at MPI in Dresden actually contributed the theory, and we've made extensive use of neutron scattering facilities, more or less wherever they will let us in. So, you know, at several different facilities. Right, so I'm going to be talking about unhappy magnets and exotic magnetism. So I think it sort of behooves me to talk about conventional magnets and happy magnets and such. And so, you know, this is the sort of standard picture of magnetically ordered phases and magnetic materials that we've had now developed over a long period of time. We have in at least insulators, you know, we would have a network, an ordered network of magnetic dipole moments that are arranged on some lattice, and because of crystal chemistry and exchange interactions, these magnetic moments, which you can think of as little arrows or little dipoles, they'll arrange themselves due to their intersite interactions, which are often described by a Hamiltonian, which is very simple. The energy just goes like the dot product between near neighbor spins. And so depending on the sign of this exchange constant out front, the near neighbor spins will either want to arrange, parallel to each other, and we call that a ferromagnet, or anti-parallel to each other, which you can see here, where every spin is anti-parallel to its near neighbors, and that's an anti-ferromagnet. Okay. And actually, the statistical physics of either a ferromagnet or a simple ferromagnet or a simple anti-ferromagnet, it's almost exactly the same problem. At least it is, so long as you don't involve quantum mechanics too seriously. It's essentially the same problem, and the same overall phenomenology happens as a function of, say, decreasing temperature. And this shows you, this is just a very simple classical Monte Carlo simulation of Ising spins. So those are spins that can either point up or down. And let's say the up ones are the black squares and the down ones are the white squares. And this is what happens as you cool the system down from relatively high temperatures to relatively low temperatures. And at high temperatures, as is always the case in any system, entropy wins out over energy, and the system is always disordered. Okay? And then at low temperatures, energy will eventually win out over entropy, because entropy contributes to the free energy like Ts, right? So if you knock T down enough, entropy will go with it. And so energy wins at low temperatures, and then you've got some phase transition in between it. Okay? So this is what happens in typical materials. And the phase transition, if you like, is the dividing line between the entropy-dominated and the energy-dominated regime. And actually, what we're interested in, and we're not the only people, there's other people in this room who are also interested in this, is looking to maintain this sort of disordered state down to the lowest temperatures. And there's a couple of reasons we want to do this, but probably the most compelling reason is that if you preclude the conventional phenomenon from occurring, it opens a window for unconventional phenomenon to occur. And so if we can maintain this disordered state not by thermal fluctuations, but by, say, quantum fluctuations or by geometrical frustration, then we can end up with an interesting quantum disordered ground state. So that's what we're ultimately looking for. And those two states, ferromagnetism and antiferromagnetism, as I mentioned, if you pick up Ashcroft and Merman or any of the standard solid-state physics books, they're almost described in the same breath, right? It's really the same phenomenology that applies to both of them, but they have vastly different histories, actually. And the reason they have vastly different histories is that a ferromagnetic material will generate magnetic field lines that build up and add up coherently and will give you a substantial magnetic field outside the material itself, and that will allow you to stick fridge magnets to fridges, for example. And also, you can make little needles out of ferromagnetic materials, and they'll align with the Earth's magnetic field. Okay? So ferromagnets, and there's a host of minerals that actually behave like ferromagnets. Ferromagnets have been known since antiquity, and actually have been used in our technology since antiquity for navigation, compass needles and what have you. And going back, more than 2,000 years in Greece, India, China, and such. But antiferromagnetism, it turns out, was only discovered in 1949. Okay? And what makes this distinction even kind of more striking is that most magnetic materials in nature, and I really mean the large majority of them, are actually antiferromagnets, not ferromagnets. So the most common form of magnetism was discovered 2,500 years after this kind of relatively niche form of magnetism. So anyway, it's an interesting history. So why was antiferromagnetism really only discovered in 1949? And it was actually postulated before that, but this was the discovery paper, which is Shull and Smart from 1949 at Oak Ridge, detection of antiferromagnetism by neutron diffraction. And these are two neutron diffraction patterns that they observed. And basically, it's a powder diffraction measurement, very simple measurement, at basically liquid nitrogen temperatures at room temperature. And they see some extra diffraction peaks at low temperatures. And those extra diffraction peaks were from the manganese dipole magnetic moments that were arranged in this antiferromagnetic structure of manganese oxide, but only below its phase transition temperature. Okay. So this occurred in 1949, and this actually required essentially the invention of neutron diffraction and neutron scattering techniques, which in turn required the invention of the nuclear reactor so that we had beams of neutrons available that were sufficiently strong that you could do this sort of diffraction experiment. So that's why 1949 is a big year for magnetism, or for antiferromagnetism. Okay. Now, it's kind of interesting that the very first antiferromagnetic structure, so the very first conventional antiferromagnetic structure, was only really understood in 1949, but almost immediately thereafter, our theory colleagues, and these are among the most famous theory colleagues in condensed matter physics, began thinking about exotic phases of magnetism, even though the conventional ones had just been discovered. You don't get a break. You can't relax for a minute. And anyway, so this shows you, these are all theory papers. So this is Vanier at Bell Labs, talking about antiferromagnetism and triangular geometries. This is Phil Anderson, made all sorts of contributions to condensed matter physics, but here he's talking about antiferromagnetism in tetrahedral geometries. And this is actually a very famous French theorist who sadly just passed away, Jacques Gaulin, who was talking about something he called insulating spin glasses in the late 1970s. And actually, here is a very famous American scientist, Linus Pauling, talking about the structure of ice. The structure of ice. So if I'm in Canada, I say ice that you skate on, but here you probably don't do a lot of skating. And so maybe the ice that floats around in your drinks. Anyway, the structure of ice is itself disordered, and we'll come back to that in a minute. Anyway, so almost immediately when antiferromagnetism was discovered, people started thinking about ways that they could screw it up, essentially. So I'm going to be talking about a class of materials that I've been studying for a long period of time. These are the cubic pyrochlores. And what's interesting, to me at least, about this family of materials is that they're cubic materials, and the local architecture of the material is it's a network of quarter-sharing tetrahedra. So you've got a whole bunch of tetrahedra here with 4 sites at a vertex, and they're connected in a 3-dimensional array such that they fill all space. Okay. Now let's see what happens when we decorate the vertices of a single tetrahedron with magnetic dipole moments, and then give them certain properties in terms of their anisotropy and their interactions. So this is going to sound a little bit contrived, but I assure you that it's quite common in nature. You can have magnetic dipole moments that are constrained by crystalline electric field effects, which I'll explain in a few minutes, such that they can only point into or out of the tetrahedron. And the magnetic moments themselves have interactions in which near neighbors would prefer to be aligned parallel to each other. So it's almost a ferromagnet, and in fact, there is a net magnetization to a single tetrahedron. It's pointing from your left to your right, okay? But it's not the magnetization of 4 of the individual spins. It's less than that because the moments are canted to obey their local anisotropy, such they can only point into or out of the tetrahedron. So you could convince yourself pretty quickly that with that anisotropy and that interaction, the best you can do on any one tetrahedron is to arrange 2 of the spins pointing in and 2 of the spins pointing out, okay, as is drawn here. But you could also convince yourself pretty quickly that there are 6 different ways you can do that on a single tetrahedron, okay? And so there's a degeneracy of 6. So if you like, the magnetization could either point, left to right, right to left, up, down, and in, out, if you like. And at any rate, so you've got this degeneracy of 6 associated with one tetrahedron, And then if you connect the tetrahedra together to fill three-dimensional space, you get a degeneracy that's going to scale very quickly with the number of tetrahedra you connect together to start filling space. And in fact, the degeneracy scales so quickly that you get what's referred to as a macroscopic degeneracy, which is a degeneracy that's big enough to give you a residual entropy, even in zero temperature, that precludes the possibility of an ordered phase. There's too many choices, basically, for the spins. And that problem that I just described is referred to as the spin ice problem. Okay? And this is the discovery paper associated with it. Okay? And you know, this is a great name, best branding in physics in my career, in my part of physics in my career. People like saying this. You know, it's appeared in the Big Bang Theory, you know, so it's legitimately famous. And it actually means something. Okay, so it obviously means spin. Okay, but it also relates to ice, and what I was talking about Linus Pauling, and that is that the degeneracy of these four spins on a single tetrahedron is the same degeneracy that exists in hexagonal ice. Now, ice has many phases, but they're basically sort of all based on hexagonal ice. And in that case, you know, this is well known to chemists, not so well known to physicists, that you know, ice is not an ordered solid. There's something ordered about it, which you can vouch for if you ever fall on it. But it's not an ordered solid. So what's ordered are the oxygen ions. The protons, the hydrogen ions, are not ordered. Okay? And the hydrogen ions have the same degeneracy. It's the same statistical physics problem as you have with this magnetism problem, and that's why it's referred to as spin ice. Okay, so almost as soon as that problem in you know, this classical problem of little arrows decorating the vertices of a tetrahedron, so that was introduced in 1998, and almost immediately, again, our theory colleagues, you know, helpfully started to think about, well, what would happen if you had that same classically disordered magnetic ground state, but you gave it Hamiltonian that allowed quantum fluctuations, that was really quantum. So, you know, you could still imagine, you know, having these magnetic dipole moments, but now, you know, not only are you going to allow thermal fluctuations, but you're going to consider, you know, quantum fluctuations. And so this has actually been very beautifully developed. Actually, you know, going back almost 20 years now. And I'm going to do it a great injustice, but I'm going to say that, you know, the main thing that you get from the quantum spin ice problem that wasn't there in the classical spin ice problem is the ability to tunnel between ground states. Okay? So that's kind of illustrated here, where we've got a little piece of the Pyrochlore lattice, you know, 4 tetrahedra. Each of the tetrahedron has 2 spins pointing in, 2 spins pointing out. Okay? But I've taken a hexagon of spins that connect these 3 tetrahedra here, and I've imagined simultaneously flipping all of them and tunneling from this ground state of the system to this other different ground state of the system. So quantum fluctuations can allow you, you know, that sort of tunneling. And actually, the theoretical development is much more involved than that. I don't think you'll be surprised. And in fact, this problem, the quantum version of this problem, is now known to possess what's referred to as an emergent quantum electrodynamics. And that is that, you know, the basic ingredients of the quantum spin ice problem are essentially the same as the basic ingredients of quantum electrodynamics, right? The quantum theory of light and such. And, you know, and the elementary excitations of quantum spin ice reflect that. There are 2 sets of gapped excitations. So this is energy, and this might be wave vector. But at any rate, there's 2 sets of gapped excitations, which we're going to call magnetic monopoles. That's the highest energy one. And either electric monopoles or bosons. You know, the field isn't quite decided what we're calling the second one. You know, some call it one, some call it the other. They're both gapped. And then there's a set of gapless excitations, which are referred to as emergent photons. So the gapless photons disperse linearly, And they also have some very interesting spectroscopic properties. And the most spectacular of these, this is theoretically predicted, this has not been observed, is that the spectral weight actually decreases as you go down in energy and vanishes at the zone center. Okay? And this is similar to the spectral properties of acoustic phonons, but exactly the opposite. Phonons are strongest as you go to lower energies, and their intensity diverges as you get to the zone center. So interesting similarities and differences. Anyway, so this has been, sort of a very not completely defined, but very attractive goal or grand challenge to the quantum condensed matter community, at least since the middle 2000s or so. And the theory is very well developed for it. Experiments, not so much, and it's not for lack of trying, so if we're looking for new materials with new ground states, new exotic ground states, we want to consider a set of materials that has a crystalline architecture that can promote disordered ground states. So an architecture like the Pyrochlore lattice, but we're trying to do that with relatively small quantum numbers so that we can get a quantum degree of freedom decorating these vertices. And so the story I'm going to tell you about today is the story of these cerium-based pyrochlores. And so in these materials, all of the magnetism is connected with the cerium 3+ ion, which resides on the blue sublattice here. Okay, so there's also, so these are magnetic. There's non-magnetic transition metal 4+ ions like zirconium, tin, and hafnium that that reside on this interpenetrating red network of corner-sharing tetrahedra. But the red network is non-magnetic, so in a minute I'm going to forget about it. I'm just showing it you here so you can see what the crystal chemistry looks like. And as I said, we've got our active ingredient is cerium 3+, which is down here in the periodic table. It's right at the opening of the 4f shell. And for cerium 3+, you've only got one 4f electron. And if you use Hund's rules, that will tell you that the total angular momentum is relatively small. It's J equals 5 halves. Now, it turns out that I've spent most of the last 30, 35 years studying not just this one particular rare earth pyrochlore, but actually most of them as you go across the series here. So it turns out that you can take out the rare earth site, so the cerium, and replace it with almost any of these other 4f ions, and it will also form this structure. And so what the field has been doing, the experimental field has been doing, is that it's been looking to see what happens if you put different potentially magnetic ions into this environment. And each of those magnetic ions they'll have a different size magnetic moment, they'll have different magnetic anisotropy, and they'll have different magnetic interactions. And that combination will conspire to give you different ground states. So now, 30 years on, we found a lot of materials with different ground states, some of which are conventional, some of which are exotic. At some level, it doesn't matter whether they're conventional or exotic. Once we've got them, we need to characterize them. But the one that we're looking for is quantum spin ice, and that's the one that seemed very promising with these cerium-based pyrochlores. So that's the one that I'm going to talk about. Okay. So these were some of our very early measurements on cerium zirconate. Very similar measurements were done by Pen Chang here. And I'm showing you inverse susceptibility versus temperature on this plot, and I'm showing you our heat capacity measurements along with Pen Chang's heat capacity measurements on an independent crystal that's shown over here. And the main thing I want you to take away from this data is just that there are no sharp features in it. Okay? So a phase transition to some sort of ordered state or some sort of frozen state would appear as a sharp feature in this sort of data and other data. And for the susceptibility, you can see, the data is in black, and it's curved, but there's no sharp features in it. And actually, the whole curve can be well understood on the basis of a Van Vleck susceptibility, which depends on you understanding the crystal field eigenstates and eigenvalues for cerium-3+, which we do, and I'll come to that in a minute. Okay, so that can be fully understood, and that's the red line. And then, as I said, for the low temperature heat capacity, which is the heat capacity associated with whatever those degrees of freedom are associated with the J equals 5/2 at the cerium site, that's giving rise to the Schottky-like anomaly, but there's no phase transition, there's no lambda-like anomaly anywhere here, down to about 60 millikelvin. Okay, so that says that this has the minimal requirements that we need for a quantum disordered state like a quantum spin ice, in that there's no obvious phase transition. If there was, we would stop there and we would do a different set of experiments. So actually so now we're going to turn to the characterization by neutron scattering techniques. So this is my real expertise. And so these are rare earth-based insulators. And one of the things that's kind of, well, I find it nice about spectroscopically studying rare earth insulators is that there's a very nice separation of energy scales in the problem. There's basically 3 energy scales in the problem. So one is the spin-orbit coupling, and we're sitting at the bottom of the periodic table, so spin-orbit coupling is strong. Okay? So that's a big energy scale. And so we've got our J equals 5/2 Hund's rule ground state at the bottom. That's going to give us, this is a Cronmer's ion with an odd number of electrons, so that's going to give us 3 doublets. Okay. And then the next excited state is J equals 7/2. It's going to give us 4 doublets there. Okay. And then we're going to have the effect of the crystal electric field. So the cerium-3+ is not in vacuum. It's not in outer space. It's sitting, 2 or 3 angstroms away from these very strongly electronegative oxygen ions. So it's feeling this very strong electronegative environment. And that's going to take these 6 states, which would otherwise be degenerate, and break them up into 3 doublets. But the crystal field energy scale is about an order of magnitude lower. It's of order 10 MeV. And then finally, we get to the level of the exchange interactions between the magnetic moments. And so this is really where conventional condensed matter physics kicks in, right? It's hard to get people very interested in my field in this, but we have to do it. But this is what they're really interested in because this determines phase behavior, elementary excitations, and so forth. But this is a much lower energy scale. This is like 1 MeV, and I just show you some spin wave measurements from one of the other rare earth pyrochlores that we've studied, erbium titanate. So at any rate, if we're going to do meaningful spectroscopy on this system, we've got to do it on all these different energy scales in order to understand things properly. And so that's what I'm going to show you. And so what I'm showing you at the bottom, so this is an inelastic neutron spectroscopy experiment where the energy scale that we're probing is about half an EV, right? 500 millielectron volts. And with it, it's not that easy to see because the thing that I want you to pay attention to is where this black arrow is pointing, is that you can see excitations within the J equals 5/2 multiplet here, but then the excitations to the next multiplet, which is J equals 7/2, are up here at about 250, 260 MeV. So we see the J equals 7/2 excited state Hund's rule multiplet for cerium-3+, and it's residing exactly where we expect it to, about 200 to 300 MeV above the ground state. So that's fine. So now we're going to step down in energy and we'll do spectroscopy at the 150 to 200 MeV level. And now we can see the splittings between the 6 states that make up the J equals 5/2 Hund's rule ground state. So it's J equals 5/2, so it's 2J plus 1 fold degenerate in the absence of a perturbation. That's 6-fold degenerate. and it'll break up into these 3 doublets, okay? And it's basically this effect here. It's the cerium 3+ ion, right, that's sitting in this, in the middle of this slightly distorted cube of oxygen 2- ions, and the oxygen 2- ions are very close. Actually, they're a couple of angstroms away, okay? And that produces, you know, these splittings that are of order, in this case, 55 MeV, okay? And so at this point, you know, this is an eigenvalue problem where you can read off the eigenvalues. Those are just the energies. So you've got the ground state, first excited state, second excited state. And then the eigenvectors are the wave functions that correspond to these crystal field states. Okay? So suffice it to say that this problem can be completely solved. And the net result, you know, right, the eigenvalues are obvious. The net result is that we can understand the wave functions that make up the ground state doublet, the first excited state doublet, the second excited state doublet. And the point that's really important here is that the ground state doublet is extremely simple. Okay? It's made up only of the z component of J equals ±3 halves, you know, in these 2 states, right? So it's not a linear superposition of all the possible, you know, MJ states. It's only one of them. Okay? So a very high symmetry state, and that will be important. Okay. So it turns out that even though we started off with J equals 5 halves, we've separated out 2 of these states from the other 4, and there's an energy difference between them that's 55 MeV, which is 500 Kelvin. So we're interested in the low temperature properties of the material, definitely below 10 Kelvin. At 10 Kelvin, you can forget about everything up here. The only thing that matters are these 2 states. And so this is what makes it a quantum problem, right? This is what gives you a small quantum number, because effectively, you know, this is what we would call a pseudo spin a half degree of freedom associated with each cerium 3+ ion. And it's just these states here, and it's pseudo spin a half because there are 2 of them. I'm going to come back to that in a second, though. So it turns out that for all of these rare earth-based insulating pyrochlores, you get the same sort of phenomenology in that you've got some relatively large total angular momentum for the rare earth site, but there's 2 states which are pulled down below everything else, and at low temperatures you can forget everything else. So you end up with a pseudo spin a half degree of freedom associated with those 2 states. And then it turns out that you can classify the nature of the doublets that you get across this rare earth series, okay? And you classify them on the basis of the symmetry of their wave functions. And they break up into 3 groups. So the group that we have most of our intuition for is the group where all the components of spin a half, Sz, Sx, and Sy, they all behave like magnetic dipoles. So this is exactly the case that I was describing before, where you imagine the little arrows right there. Those are all behaving like magnetic dipoles. Okay. Then you can have the case that we're going to be interested in now, where actually 2 of the components will behave somewhat like magnetic dipoles. Well, one of them behaves exactly like a magnetic dipole, Sz. Sx and Sy both behave like octopoles, but Sx actually transforms like an octopole. I'll have to explain what that, like a dipole. I'll have to explain that in a moment. So that's referred to as a dipole-octopole pseudo spin a half degree of freedom. And then the last possibility, which I'm not going to be talking about, is a case where Sz or Sz transforms like a dipole, but Sx and Sy transform like quadrupoles. Okay. And actually, this has been known for a long period of time, but it wasn't known to myself and a large part of our community until, I would say, about 10 years ago, that we realized that these pseudo spin a half degrees of freedom that we were, talking about, they didn't necessarily have to behave like magnetic dipoles. Okay? They were spin a half degrees of freedom, but they didn't have to behave like magnetic dipoles. Okay, so whether these different components of spin behave like a magnetic dipole or not, it depends how they behave in relation to the different symmetry operations that you can perform at the cerium 3+ site that maintain its point group symmetry. Okay? So it depends on the point group symmetry at the cerium site and time reversal symmetry. Okay? Yes?
First, what would change here if you had a spin 1 instead of spin 1?
Yeah, so if it was spin 1, then you would definitely be in this regime here. Actually, any integer spin, you would definitely be in this regime here, because you can only get that with an even number of electrons, right? And so then you can still have the pseudo spin 1/2 degree of freedom, but in that case, the x and y components of the pseudo spin 1/2 degree of freedom definitely are quadrupoles. And I think it'll become more obvious. I'm going to go through and describe the dipole octopole case, but if you understand that, you'll also understand the other one. But it's but that case definitely has to be this non-Kramers case where 2 of the components are quadrupoles. So that would, yeah, and you can see that is relevant for both terbium and praseodymium. Okay, so let's look at that in a bit more detail. So we've got these 2 low-lying states that are separated by all the other states by some large energy scale. So we're going to forget about all these high energy states. Okay? And this could happen in a system which only had a spin degree of freedom, okay, where say orbital angular momentum was quenched, or maybe it was 0 from the outset. And in that case, so real spin 1/2 has a total spin quantum number of 1/2, and its Z component or Z component is either plus or minus 1/2. So you're making transitions between these 2 states from spin up to spin down, and you can do that with one spin raising or spin lowering operator, right? One of those will do it, okay? But that's not what we have to play with. So what we have to play with in our pseudo spin 1/2 degree of freedom, these 2 states, you've got a total angular momentum of 5/2, and the 2 Z components that make it up are plus or minus 3/2, okay? So you can still define these operators, an SX operator, so pseudo spin 1/2 X operator, pseudo spin 1/2 Y operator, and pseudo spin 1/2 Z operator, okay? But the pseudo spin 1/2 Z operator, if you look at its expectation value, within either of these 2 states, you get a non-zero number, and so that's saying that SZ behaves like a dipole operator, so SZ behaves like a dipole. But SX and SY are the operators that are required to go between these 2 states. They're the operators that are required to go between, say, MJ equals minus 3/2 and MJ equals plus 3/2. And the only way you can do that is not with a single raising and lowering operator, but with 3 raising and lowering operators, because you've got to go from minus 3/2 to minus 1/2 to plus 1/2 to plus 3/2. So, the relevant raising and lowering operators are actually made up of 3 of these, in this case, J, total angular momentum, but it's JX or JY operators. So SX and SY, pseudo-spin SX and SY operators are actually made up of a product of 3 dipole operators, which makes them an octopole operator. So how are we going to think about these degrees of freedom? Because we can't think of them as little arrows anymore. Or, well, we can still think of the Z component of spin as a little arrow, but we can't think of the X and Y components of spin as a little arrow. So what we're going to do is we're going to take the F electron orbitals that we're familiar with. So these are L equals 3 orbitals, and we're just going to write them out here. And these are, so there's 2L plus 1, there's 7 of them in total. And, some of these actually look like octopoles. Like this one looks like 8 poles, this one here looks like 8 poles, okay? We're not going to be using those. And the ones that we're going to be using are the ones that are consistent with the point group symmetry at the cerium site. And that's this one here, and this one here. And the reason we're using these is that they have a 3-fold rotation axis about the Z direction, okay? So in fact, this one is just this one rotated by 90 degrees about the Z direction. So we're going to use one of these as Sx and the other one as Sy. So Sz is going to be described as a dipole, which now instead of drawing it as an arrow, I'm drawing it as this two-lobed object with a red and a blue lobe. So that's a point and a tail. And Sx and Sy are going to be this particular L equals 3 octopole. This particular L equals 3 orbitals, right, which are octopole orbitals. And it turns out that the most general Hamiltonian that we can have for this problem, okay, is one in which the Sx, Sy, and Sz components of the pseudospin half degree of freedom, they enter independently in the Hamiltonian, okay? And it turns out that we can mix the Sx and Sz components of pseudospin, because actually those two, so even though the Sx operator corresponds to a magnetic octopole, okay, it transforms as if it was a dipole. So the fact that it transforms as if it was a dipole means that in the most general Hamiltonian for it, we can mix the Sx and Sz components of spin, but we can't do anything else. Okay. So this is the most general form of the Hamiltonian, and it's referred to as an XYZ Hamiltonian. And so this is the sort of cartoon that you might carry around. It's not going to be useful for really anything other than as a educational prop, I guess. But the basic idea is that we're going to be decorating the vertices of these corner-sharing tetrahedra, and we can imagine, that you've got magnetic dipoles which are coexisting with magnetic octopoles along the same lattice, that they correspond to different components of the pseudospin half degree of freedom. And the Y component of spin is definitely an octopole, which transforms like an octopole. But if you rotate along the Z direction, you get a dipole. So this is really, this is not going to be so useful in any real development, but it is useful to sort of visualize these things. Okay, so here I am, well into the presentation. I'm only now getting to the low energy physics, which is the part that most condensed matter physicists care about. And I'm showing you our low energy experiments now on cerium zirconate. And so now instead of doing spectroscopy at 500 MeV or 150 MeV, I'm doing spectroscopy below 1 MeV. Okay. And I'm actually taking data, and I'm just looking at all the data as a function of energy and the modulus of Q. And these are measurements on a single crystal sample. But really what I want to do, I just want to see where the intensity is greater at low temperatures than it was at high temperatures. Okay, and these are all, I don't know how well you can read it, but these are all the difference in data sets between a low temperature and a high temperature. And what you can see is that there's basically no difference or very little difference in the elastic channel. But then as you go from the elastic position up to 0.2 MeV, that's where the extra spectral weight resides. Okay? And so we can integrate this up in energy and look at its Q dependence, look at its momentum transfer dependence in a neutron scattering experiment, and we get this result here. So this is unpolarized inelastic scattering giving us a structure factor. And the structure factor is diffuse scattering. There's no Bragg peaks here. There's even no elastic scattering here for that matter. But this sort of pattern is very similar to what's imagined and what's calculated actually for the classical spin ice problem, which has now been around for the better part of 25 years, so very good calculations for it. And this is one version of a quantum spin ice problem, which kind of has a structure factor that looks like classical spin ice, but it's a little bit fuzzier, as you might have guessed for a quantum version of the same problem. So at any rate, this sort of diffuse scattering pattern is somewhat of a fingerprint, for this type of quantum disordered ground state. And then we've done all sorts of experiments, but only other one that I'm really going to show you is, yes, please?
It looked like the quantum, I guess, the theory plot had a different symmetry than the other two. Am I imagining that? Like the top and bottom are darker than the...
Here, sorry?
Yeah.
Yeah, so these I think are pretty much, so, right. So along the OOL direction, it's different than along these directions here. And actually, so all of these plots for that matter, you've got, so this is the OOL direction in reciprocal space. This is the HHO direction in reciprocal space. So this is an OOL direction, but this here is an HHH direction. So there's nothing requiring them to be the same. They do look the same, but there's nothing requiring them to be the same. And so you get extra intensity there and there. And actually in the experiment. Sorry?
Are they the same in the classical?
In the classical case, they are the same. That's right, but they don't have to be. There's no symmetry reason why they have to be. Because it's different directions in reciprocal space. And then this is a similar but not the same experiment. So this is diffraction, but spin polarized diffraction, performed in so-called spin flip mode. So this is where the neutron is being diffracted from the sample, but it's going from spin up to spin up, or spin down to spin down. Oh, sorry, this is spin flip, so it's going from spin up to spin down. And in this case, it's going from spin up to spin down. Okay. And actually, one of the interesting things about doing this sort of measurement, first of all, it's integrating over all energies. Okay. And secondly, we can compare it to what's known to happen in, actually, I think a system that there's almost no disagreement that this is a classical spinite, and this is holmium titanate. And this is a very famous paper, published about 14 years ago, showing the same measurements for classical spinites. And you can see, the similarities and differences, but they're pretty significant. You get the snowflake-like pattern where you have, these things here in the measurement of holmium titanate, they have these things that are called pinch points. So the diffuse scattering, you've got this blobby diffuse scattering, and it comes together and just touches at a single point. And that's referred to, I think my pointer has run out, and that's referred to as a pinch point. And we also get a pinch point in our measurements here, right there, but it's a fuzzier version of the pinch point. And it's a fuzzier version of the pinch point. And once again, whoever was asking that earlier question, you can see that it's not present along the HHH directions. Awesome, thank you. Great. Great. Yeah. Yeah, perfect. Yeah, no, that's fine. So anyway, so this problem has been of interest to theorists like Andre and others. And at this point, it's actually theoretically pretty well understood, actually. So this is another way of writing down this XYZ Hamiltonian. And here, so X and Y and Z all contribute independently to the Hamiltonian. But SZ and SX can mix, as I was saying before. But here we're mixing them in a slightly different way. We have this mixing angle theta that we add to the Zeeman-like term. At any rate, so this is the Hamiltonian I'm going to use from now on. But this is the general phase diagram for this system. And actually, it's a very attractive phase diagram from an experimental point of view. And that's because a lot of this phase diagram, actually everything above the line that I'm tracing out here, are quantum disordered ground states, right? So these are all versions of quantum spin ice, but their quantum spin ice where either the dipolar degree of freedom or the octopolar degree of freedom dominate. And those basically dominate depending on which of Sx or Sy dominates or is bigger, right? Which of those two terms in the Hamiltonian is bigger. And then at the bottom, you've got these more conventional ordered states. But you can have either the dipoles ordering or the octopoles ordering. So you can have conventional ordered states that are driven by either dipoles or octopoles, and you can have quantum disordered states which are driven by either dipoles or octopoles. And so now what we would like to do is we would like to place cerium zirconate somewhere on this phase diagram. And if we were dealing with a system that only had magnetic dipole moments, then this would be, well, it wouldn't be easy, but we know how to do it. Okay, and what we would do, the gold standard for estimating spin Hamiltonian for magnetic dipoles, okay, is to measure the spin waves in the system and then fit the spin waves to spin wave theory or some more sophisticated version of spin wave theory and back out the exchange Hamiltonian. And so, you know, we've kind of made a career out of doing this sort of thing. So here's some early work out of, you know, a different pyrochlore and another different pyrochlore. And you know, if you don't have, you know, sharp spin waves in zero field, you can apply a field and get sharp spin waves. Or you might start off with sharp spin waves and you can get different sharp spin waves in the field. Anyway, that's the gold standard. That's what we would really like to do. But we can't see well-defined spin waves either in zero field or in a field in this material. And it's pretty much got to be because of the octopoles. The octopoles, we're not coupling strongly enough to the octopoles to see the spin, whatever, you know, would be the equivalent of spin waves in such a system. So what we can do is do a sophisticated analysis of everything else that we've got. And everything else that we've got are thermodynamic measurements, so heat capacity, magnetic susceptibility, and those diffuse neutron scattering patterns. Okay. And so, you know, here's our low temperature neutron scattering, our low temperature heat capacity. You know, this is all due, this is at sufficiently low temperatures that it's all due to those pseudo-spin degrees of freedom on the cerium site. We get together with our theory friends, you know, in this case at Dresden, and they perform this calculation, which is referred to as a numerical link cluster calculation. And it's a finite size, it's an exact calculation on a finite size lattice. And the finite size lattice in this case is 7 tetrahedra. Okay, that's as good as they can do. And it works kind of like a high temperature series expansion works, that it will give you accurate results, you know, so long as the correlation length in the real system is shorter than the system size that you're doing the calculation on. Okay. So it's shorter than 7 tetrahedra. And actually, so the best fit green line is shown here. It doesn't agree at the lowest temperatures. That's probably for a couple of different reasons. But it does provide a very good description, you know, in the region where it's supposed to provide the good description. So, so we actually you know, use this. I'm not going to show you all the analysis that we did, but we did similar modeling of magnetic susceptibility data and diffuse neutron scattering data. You know, and the bottom line is that, you know, we have, you know, for this system, we've got no evidence of long-range order, no freezing above about 80 millikelvin, and we can back out these estimates for the terms in the microscopic Hamiltonian. And I would just say that I'll come back to this in a moment. We can also account for the form of the heat capacity as a function of applied magnetic field, but I'll come back to that. And we can also account for basically all of the R log 2 entropy that's associated with that pseudo-spin a half degree of freedom. But I think in the interest of time, I'm going to move on. So at any rate, this is now showing where that sort of analysis puts cerium zirconate according to our measurements on our crystals. There's actually 2 dots here. You know, one is our analysis in zero field, and the other is our analysis in finite field, and they agree very well with each other. But actually, what's in some ways more amazing is independent work by Penchang Guy's group with Andre and such on a independently grown crystal, independently done and analyzed experiments, put cerium zirconate not exactly at the same place, but pretty close by. And I consider this to be actually very, very good agreement. But where we're putting cerium zirconate is far removed from any of the ordered states, and actually, you know, essentially on the border between an octopolar quantum spin ice and a dipolar quantum spin ice. And so, you know, I think that's a, you know, these fields, they never stop evolving, right? So I, you know, never say never. But, you know, the status when I made up this plot was pretty good agreement. And then we can do other things that would corroborate this. So we can look at cerium zirconate in an applied magnetic field. And there's actually a very interesting and easy to understand argument about any spin ice in a magnetic field where the magnetic field is along the 110 direction. So this is a little piece of the pyrochlore lattice. And this red direction here is a 110 direction. You can think of the pyrochlore lattice as being made up of these interpenetrating chains that point along a 111 direction, those are shown in red, and those that are perpendicular to a 111 direction, to that same 111 direction, and those are shown in blue. And so the red chains are referred to as alpha chains, the blue chains are beta chains. And what's interesting is that for any spin ice where you have a Z component or a Z component of spin that is pointing, you know, like in, out, like this, a magnetic field along the alpha chain will polarize the red chains. Those will all get polarized to the extent possible. So the spins will all cant along the spin direction, along the field direction, and it will decouple the beta chains. Okay, so it polarizes the alpha chains and it decouples the beta chains. So the polarization of the alpha chains leads to new Bragg peaks, which you can see at low temperatures and finite magnetic field, and this is such a Bragg peak here. It's not present at low temperatures and zero field. It's not present at high fields. Now, this is kind of the only new Bragg feature that shows up in this window of view. And you can look at the field dependence of that peak, and that can even be quantitatively described by an appropriate theory that's related to this, that's related to the numerical link cluster work and that sort of thing. Actually, there's another Bragg peak which we also followed, but so these Bragg peaks are direct proof that the alpha chains are polarized, and then the beta chains are kind of left hanging. You've got these independent beta chains which aren't affected by a field at all, and so they aren't affected by a field at all because the moments are perpendicular to the field, so they just stay as disordered one-dimensional chains, and they give rise to this sort of diffuse scattering. So this sort of diffuse scattering, it's structured, it's actually quite weak, as expected, it's structured, but it also comes out of the board, right? It forms a plane of scattering, which is modulated to some extent. You can see the modulations. But you know, there's a plane of scattering that comes out of the board, and that's the signature of these decoupled beta chains. Okay? So this system is behaving in a 110 field as you'd expect a spin ice to behave. Okay. And its heat capacity, I mentioned I was going to come back to this. The heat capacity in a field, in a 110 field, also behaves as you would expect a spin ice to behave in a 110 magnetic field. And that this is the heat capacity on a logarithmic scale now. So this is in zero field here in blue, and we can describe it quite well with that theory that I was showing you. Okay? And then as you crank up the field, we're not cranking it up very high, only to 2 Tesla, but actually what happens is that the contribution or the magnetic heat capacity splits into 2 pieces. One piece sharpens and moves up in temperature, and the other piece is unaffected. So the piece that sharpens and moves up in temperature, that's due to the polarized alpha chains. The piece that doesn't change at all is due to the beta chains, because the beta chains are unaffected. So again, this behaves exactly as we expect the spin ice to behave. Okay. So that's where I'm going to end the story now. Of course, the story isn't ending, right? It's you know, there's still all sorts of interesting things going on with other cerium pyrochlores and with other systems which are candidates for quantum spin ice, disordered quantum ground states. But actually, I would argue that the cerium zirconate probably at the moment is the best case for you know, something, you know, really resembling a quantum disordered ground state with no complicating freezing or other ordering, and at that a quantum spin ice version of a disordered quantum spin liquid. And so I'll just finish by putting up. I'm not going to put up pictures of all of our collaborators because there's too many of them. So I'm only putting up the most photogenic, which are the youngest. And also, these 5 papers basically describe everything that I've discussed and a little bit more. So thanks very much.
Thank you so much, Bruce. Questions?
So I didn't quite catch what the origin of the cusp is in the heat capacity.
The origin of the cusp. Oh, so it's basically right. You mean just the fact that it goes up,
Yeah.
comes down, right? So it has to come down. It's got to eventually go to 0, and so this is maybe a better picture to look at here. So it's all the same data. Everything in blue is the same, and so this is the fit to the theory that I was talking about before. And then down here we've got an extrapolation of the heat capacity to go down to 0, which it has to do because the integral of C mag over T from 0 to T, is the entropy as a function of T. And when we get up to high temperatures, that's got to give us R log 2 because that's the number of degrees of freedom that you have in the ground state. So we have to account for R log 2 in entropy, and it has to go to 0. And so the only extra thing that you could put in here in principle was you could say, well, maybe there's a phase transition down here, in which case there'd be another peak. But actually there isn't much window in entropy for another peak. There's not much unaccounted for entropy. But the reason it's a peak here, it's just the scale of the exchange interactions. They kick in somewhere around here. They start to have an effect somewhere around here, and the heat capacity and the entropy have to go to 0 at 0. So that's why there's a peak in between.
So you can basically say, establishing some sort of quantum coherence, right? About the temperature for a piece. Due to
You could make that sort of argument. And in fact, the argument that we did make in one of our papers, and this is just an observation, it's not really, is that if you take the heat capacity from the peak in our measurements, which is right there, and you integrate that up, you actually get the so-called Pauling entropy, right? So there's in classical spin ices, you have this missing entropy at low temperature, and the missing entropy is the difference between R log 2 and what you get if you order all the tetrahedra up into 2 spins in, 2 spins out, but you don't do anything else. And so this is famously calculated by Pauling for proton disorder in ice, and you get that with a plateau in the heat capacity. So here there's no plateau, but if you go from the peak, you still get that result. Yeah.
So I'm not in your field, but my ears perked up on this slide when you were saying that this NLC7, that you could calculate it up to 7 tetrahedra, but not more. So what limits that? Is it a computational problem, or is there some physics limitation?
No, well, so I'm not the right person to address this. Actually, Andre probably would give a better answer. But it's just a computational complexity, and I'm told that even at the NLC7 level, that this is very difficult. So
how does it work roughly?
Yeah, so it's just that it gets much, as you make your finite system bigger, it gets much more difficult. And that scales as a relatively high power of the number of tetrahedra. But I would just say that there's a let me see if I can find it. Yep. Oops, I'm going the wrong way. Sorry. Yeah. So you're looking at finite size systems, sort of like this here, and you can see that it's actually important to get beyond 6. Okay? And because this is an arrangement of neighboring tetrahedra in the Pyrochlore lattice, and here we've got 6 tetrahedra. Okay? And if you've got 6 tetrahedra, 6 interconnected tetrahedra, you actually close this interior hexagon of connected spins. And so if you do a calculation on 6 or more tetrahedra, you're thought to be capturing all the relevant, well, a lot of the relevant physics, at least at these sorts of short distances. Whereas if you do the calculation at less than 6 tetrahedra, you're leaving out one or more of these, and so you don't have whatever physics would come from the hexagons. So I'm not the theorist that did this, but I'm told that there's a high priority on getting beyond 6, and so once you're beyond 6, then they can collapse. So they got to 7. And that was it.
So
Function.
I'm actually curious, can you show the phase diagram where you sort of put the parameters of?
Yeah.
So how do you actually? So you believe that the parameters of serum 227 is right in between? How do you experimentally really separate whether it's octopolar or dipolar quantum spin liquid?
Yeah. So at some level, I would say it doesn't matter. There are interesting things associated with being close to this boundary, but you have anywhere in the neighborhood of here, you have very significant dipolar and octopolar correlations, right? So you've got them.
So do you expect the pinch point in both cases, or?
You expect you can, yeah. You have to do the calculations to see, but certainly any variation like this, the changes in the diffuse scattering will be minor. So, things vary, but the big variations are when you cross from a
Sure.
disordered state.
But yeah, we're sort of in agreement that the serum gluconate is not in the ordered state.
Right.
Okay. Thank you.
So in your clinical now, may suggest that we convene for winding machines outside this room. This will be around.
Yeah. My understanding that basically that